Hi there again. Here's another MATLAB script that we use here at Al-Sheikh to basically identify or approximate the total noise figure of a device under test, except this time you'll need only two instruments to achieve. You have a spectrum analyzer, a power supply, basically a fully utilized power supply. You have three channels, one for the calibrated noise source, your device under test, and the other would be for a second stage amplifier. What you do here is apply the Y factor method. There's plenty of sources that would explain how that works, so I'll skip the technicalities for now and head over to the code to explain how it works. So the code here is fairly explanatory again, with a couple of comments to detail what each line does. It utilizes the instrument control toolbox again to communicate with both the power supply and the spectrum analyzer again, and average out several hot and cold readings before processing them through the Y factor method. Now, hot readings would mean that the average readings are taken when the noise source is on, and the cold readings are averages taken when the noise source is off. This requires that your noise source to be calibrated and your instrument to be sensitive enough to the difference of hot and cold readings. Let me run the code as I explain it here for you to buy us time. It starts initializing the power supply channel voltages to 28, 5, and 5, just like here. And this obviously corresponds to the required voltage by the noise source, the DUT, and the second stage amp. And then it starts to average out readings off of the spectrum analyzer, and it tells you here that it takes about 18 seconds to do that. Now, the averaging meant here is the number on the very top that is counting. It reaches 100 and repeats again. And this 100 is actually provided here in the user-defined variables section. Now, this would be done again based on the number of passes, so the higher the number of passes, the more accurate the average of the averaged readings become. Mind you that you also need to enter the excess noise ratio values that are printed on the noise source here. It's a little bit washed out in our case, but we managed to enter that. And a matrix right here, just like any other matrix, these are the frequency values and their corresponding excessive noise ratio values. You'll also need to have known noise figure values for the second stage amplifier in this case. And of course, if you don't have that already in the data sheet, you can request the manufacturer to send you that. Since this is done, let's take a look at the results. They took around 74 seconds to be done. You have a noise figure value of around 1.3 out of 2 passes. Each pass read one read 1.2, the other 1.4. So you see there's a little variance in there. Remember, this is an approximation, and the higher the average, the better the approximation, as I mentioned. Also remember that this is not going to compete with a dedicated noise figure analyzer and will not be able to tell noise figure differences of 0.1 and 0.2 dBs. This kind of accuracy is pretty hard to obtain. Things get pretty random here and hard to control. This is a known issue. That's why noise figure analyzers are pretty expensive. But you will be able to tell between 0.5 or 0.6 dBs of difference fairly accurately. So I hope you learned something from this video and could hopefully appreciate how MATLAB can actually automate such work with minimal syntax. Otherwise, this would take literally hours to be done, and this is what have taken me before having this code ready. Thank you very much for watching, and have a great day.